Hello everyone. In this video, we are going to solve the problem number 1.65 from Irodov, and that is related to dynamics. So let us first understand the problem and then we will solve the problem step by step. We are having a plank of mass m1 and the bar of mass m2. The entire system is sitting on the surface which is having the coefficient of friction is equal to 0, and the bar is sitting on the plank and where the friction between bar and the plank is given as k, which is the coefficient of friction. Now a time dependent force is applying to the bar and we have to find out the acceleration of plank and acceleration of bar as a function of time, and we also have to plot these functions. So let us first draw the free body diagram of plank and bar. So this is bar of mass m2 and a force F is equal to at is applied, and in the downward direction we will have the gravitational force of m2 into g, and in the upward direction we will have the normal reaction from the plank, and let us say this is the friction small f. And if we draw the free body diagram of the plank, then this is plank of mass m1, and due to the third law of Newton, this particular force will act in this direction on the plank because of action and reaction forces, and in the downward direction we will have the gravitational force of m1g, and in the upward direction we will have the normal reaction, let us say n1, from this particular surface, and then from the top we will have the normal reaction of n. Now before analyzing this particular friction, let us take an example. Let us say this is a box which is kept on a surface where we are having some friction. The mass of this particular box, let us say 10 kg, and the coefficient of friction here it is given as 0.2. Okay, now if we draw the free body diagram of this particular box, then let us say in the downward direction we will have the 100 Newton of force, that is the gravitational force, and then in the upward direction we will have the normal reaction. And let us say if the body is moving in this particular direction, because as we are applying the force in this direction, then the friction will act in the opposite direction of the motion of this particular box. Let us say this is F. Now let's say this is capital F that we are applying. If the capital F is equal to 0, then what is the friction? The friction force will also be 0. That means if the box is at rest condition, then there will be no friction in this particular box. Okay, let us say if we are increasing the force to 5 Newton, F is equal to 5 Newton, then what is the friction acting here? That we have to decide first. For that, let us find out the limiting friction. We know that limiting friction FL, let us say, is equal to mu into N. That is equal to mu is 0.2 and N here is 100 Newton. So we can say the limiting friction is 20 Newton. Okay, if limiting friction is 20 Newton, then we can say the friction here will act that should be less than or equal to limiting friction, which is given as 20 Newton. So the force cannot be more than 20 Newton. It will be maximum of 20 Newton, but if we are applying the force that is less than limiting friction, then the friction will also be equal to this particular force only. That means if we are applying 5 Newton here, then the friction force will be 5 Newton. Let us say if we are applying a force of 10 Newton, again it has not crossed this particular limiting friction, so the friction value will be 10 Newton. If we are applying F is equal to 20 Newton, then it is just equal to the limiting friction and it will be the same, that is F is equal to 20 Newton. Let us say if we are applying the force of 30 Newton, in that case limiting friction cannot be greater than 20 Newton, or the friction will be 20 Newton only. So in this particular case it will have the 20 Newton. In all three cases that we have mentioned here, the box will be in the static condition. Static condition, the box will not have any relative motion. But if we talk about here, we will have the net resultant force of 10 Newton in this direction, so that we will get some sort of acceleration. So this is called the dynamic condition. Dynamic condition, and in case of dynamic condition, we will have the dynamic friction. Dynamic friction, which is equal to mu into n. And in all static condition, we can see here that the body is in the equilibrium condition and the friction force is equivalent to the force that we are applying. Okay, now let's come to our problem. So here, as f is the function of time, as t is increasing, the force is increasing. So it will take some time to reach the limiting friction. Okay, and then only there will be the relative motion between mass m2 and mass m1. Okay, let us say this is the time t naught at which force is crossing the limiting friction. Okay, before that, the force, this particular force will be equal to this one. And so if we see here, let us say this is force F, that is equal to AT, and we will have the friction force here, and this is mass m2. If we draw mass m1, then we will have the friction force here. Now if this is in the static condition, then there will not be relative motion between mass m2 and mass m1. So if we talk about the definition of friction, then friction will always act in the opposite direction of relative velocity. Now in this particular condition, this F is the static friction, and because of that there will be no relative motion between m2 and m1. And if there is no relative motion between m2 and m1, then m2 and m1 both will move simultaneously. So both these system will move simultaneously. Okay, and as we are applying force is equal to AT, and there is no friction between this particular surface and the entire system, so we can directly write force is equal to AT is equal to total mass, that is m1 plus m2 into w, that is the acceleration. So from here we can find w is equal to AT whole divided by m1 plus m2, which is equal to the acceleration of mass m1, that is equal to acceleration of mass m2, is equal to AT whole divided by m1 plus m2. So this is the condition for t less than t naught, because for t less than t naught, there will be no relative motion between these two masses, and the combined mass m1 and m2 will move with this particular acceleration. Now let us talk about the case for t greater than or equal to t naught. Basically, if it is crossing this particular time, that means it is going in the dynamic condition. The meaning of dynamic condition is not that the body is started moving. The meaning of saying dynamic condition here is there is the relative motion between body 1 and body 2. With respect to friction, I am talking about here, right? So let us draw the free body diagram of mass m2. So this is mass m2. We are having the force is equal to A into T, and here we are having friction force that will be equal to mu into N, and the gravitational force in the downward direction, that is m2 into G, and the normal reaction in the upward direction. So, and let us say it is having the acceleration of W. So we can write force minus friction force is equal to m2 into w2, and then force we can write it as at minus F is mu into, and we are having m2 into g. m2 into g is equal to m2 into w2. Let us say this first equation we are having. Now let us draw the free body diagram of mass m1. So this is mass m1. We will have the friction force in this direction, friction force in this particular direction, that is equal to mu into n is equal to mu m2 into g, and there is no other forces in the horizontal direction. And let us say we are having the acceleration of w1. Okay, so we can write mu m2g is equal to m1 into w1. So let us say this is our second equation. Now if it is in the dynamic condition, then there will be the relative motion between mass m1 and mass m2, and if there is the relative motion between these two body, then definitely we will have w2 will be greater than or equal to w1. Okay, for the limiting case, let us equate w2 is equal to w1, and we can write mu m2g whole divided by m1 is equal to at minus mu m2g whole divided by m2. So from here we will get mu m2 square g whole divided by m1 plus mu m2g is equal to a into t, and we can write at is equal to mu m2g as common, and we can get m2 plus m1 whole divided by m1, and we will get t is equal to mu m2g times m2 plus m1 whole divided by a times m1. So this is the time t naught, before which both body will not have any relative velocity, but after time t is equal to t naught, the both there will be the relative motion between mass m2 and mass m1. Now let us find out the acceleration of these two bodies. So from here we can write w1 is equal to mu m2g whole divided by m1, and the acceleration of mass m2 we can write it as w2 is equal to at minus mu m2g whole divided by m2. So this is the acceleration of mass m2, and this is the acceleration of mass m1 for t greater than or equal to t naught. Okay, so let us write the acceleration function again. So we can say for t less than t naught, we will have the w1 is equal to at upon m1 plus m2, at whole divided by m1 plus m2, and for t greater than or equal to t naught, we are having w1 is equal to mu m2g upon m1, mu m2g upon m1. So this is the acceleration for mass 1 we are having. Now let us talk about for mass m2. For t less than t naught, we are having w2 is equal to at whole divided by m1 plus m2, and for t greater than or equal to t naught, we are having the acceleration of that we have found out here at minus mu m2g upon m2. So at minus mu m2g whole divided by m2. So this is the acceleration function we can write for mass m2, and this is the acceleration function for mass m1. Let us find out the whether both the acceleration are equal at time t is equal to t naught. So if we substitute here at time t is equal to t naught, we can write w1 is equal to at whole divided by m1 plus m2, and let us substitute t is equal to t naught. So from here we can get a times t naught we have found out here, that is mu m2g times m2 plus m1 upon a m1. So we can write mu m2g times m2 plus m1 whole divided by a times m1 into m1 plus m2. So m1 plus m2 will get cancelled. So we will get from here mu times m2g whole divided by m1. This is what the acceleration we can get at t greater than t naught. So if we draw the acceleration of mass m1 with respect to time, then let us say this is acceleration w1 and this is time. This is acceleration w1 and this is time, and let us say this is t is equal to t naught. So from here to here it will vary linearly, and after that we can see that this is constant. And what is the constant value? That is mu m2g whole divided by m1, and it is varying linearly, and the slope of this particular thing is a upon m1 plus m2. A upon m1 plus m2. This is the slope, because here if we see y as a function of time, then y is equal to some constant into time, that is y is equal to mx kind of thing we are having, and m is a upon m1 plus m2. Okay, and then after t is equal to t naught, this particular value is constant. So the acceleration of mass m1 will vary linearly from t is equal to 0 to t naught, and then it is constant. Now let us talk about acceleration 2. So if we say at t is equal to t naught, w2 from this particular thing we can say it is mu times m2g upon m1 that we have found out here. But from this particular expression, if we find w2, that we can write it as a times t is mu m2g times m1 plus m2 whole divided by a times m1 minus mu m2g whole divided by m2. So let us write it here. So w2 we can write it as a times mu m2g times m1 plus m2 minus mu m1 m2 ag whole divided by a times m1 m2. So from here we can get a times mu m1 m2g plus a times mu m2 square into g minus a times mu m1 m2 into g whole divided by a times m1 m2. Okay, so this particular thing will get cancelled, and a will get cancelled, m2 will get cancelled. So from here we will get mu m2g whole divided by m1. This is the acceleration at t is equal to t naught. So at the time instant of t is equal to t naught, we are having the same acceleration from these two values. So that means the graph is again continuous. Okay, and but the slope here is changing. If you see here this particular case, we can write y is equal to m times t, where m is the slope, and that is given as a upon m1 plus m2. And if we write here, we can say y is equal to mt plus some constant, and m here is a upon m2. Okay, so the slope here is more as compared to here, because a times m1 plus m2 is less than a times m2. Okay, so if we draw the graph between w2 and time, then it will vary linearly, and initially the slope will be less. Okay, and then the slope will increase. So let us draw it here. So this is w2, this is time. So the graph will vary linearly, and initially the slope we are having, that is a upon m1 plus m2. So the graph will vary linearly like this, and then after that the slope will increase and the graph will vary like this. So this is the time at t is equal to t naught. Here we are having the slope of a upon m1 plus m2, and here we are having the slope of a upon m2. Okay, so I hope the entire procedure is clear. Thank you.